Hello everyone, I'm Sahishnu Manohar from Computer Science Engineering Department here to present my tech talk on data structures. The topic I've selected for my tech talk presentation is array and data structure, algorithms and data structures for new models of computation. Let's begin. Let's move on with the introduction, a brief introduction on arrays and data structures and what all we are going to cover in this presentation. Array and data structures, algorithms and data structures for new models of computation, importance of efficient algorithms and data structures in new models of computation, overview of topics to be covered in the presentation. Let's begin with the classification of data structures. Data structures can primarily be divided in two types, primitive and non-primitive. Under non-primitive, there are again two types, which is linear and non-linear. Primitive data types, data structures, consists of integer data structure, character data structure, float data structure, string data structure, and double data structure. As we know, non-primitive is again divided into two types, which is linear and non-linear. Non-linear data structures consist of array, queue, stack, and linked lists, whereas non-linear consists of tree and graph. Let's begin with arrays. What are arrays? Arrays are fundamental data structure used to store elements of the same type. They provide constant access to elements using an index. Arrays have fixed size and contiguous memory allocations. Again, arrays are divided in two types, which is one-dimensional array and multi-dimensional array. One-dimensional array includes a single size, whereas multi-dimensional consists of rows and columns. This it can be used to create matrices. Basic operations on arrays. Accessing elements. Retrieving the value of an element using its index is one of the primary and most used property in arrays. Next is insertion. Adding an element at a specific position, shifting other elements if necessary. Deletion. Remove an element from specific position, shifting other elements if necessary. We use loops in, as you can see, we use loops in arrays over various many locations. Common array algorithms. There are some common array algorithms, which is linear search, binary search, and sorting. Let's begin with linear search. Linear search sequentially checks each element until a match is found. So, each element in an array, given array, is traversed and traversed and traversed again and again from each element. It covers each and every element from starting to end and finds the element and returns the element. Binary search divides the array in half and compares the target value with the middle element. So, what happens is binary search is um, it splits the array into half, and from the middle element, if the checks the given input is greater or lesser, if it's greater it goes to left side of the array, if it's yeah, lesser it goes to the right side of the array and finds the element and returns the element. Next common array algorithm is sorting, rearranging array elements in a specific order such as ascending or descending. Again, in sorting there are many types such as bubble sort, insertion sort, and selection sort. Dynamic arrays. Dynamic arrays are resizable arrays that can grow or shrink during program execution. They allocate memory dynamically, allowing for efficient memory utilization. Dynamic arrays are implemented using techniques like the size, like doubling the size, or using amortized analysis to minimize resizing operations. Here is a graph which denotes nth element inserted in the x-axis and number of cumulative copies in the y-axis. As you can see, it's steadily increasing by size 1, and big O of n, the time complexity, sorry, the space complexity is increasing as we go further. Let's start with the main topic, which is introduction to data structures. Data structures organize the store data in specific way for efficient access and manipulation. They allow for implementation of complex algorithms. Examples include linked lists, stacks, queues, trees, and graphs. Let's start with one of the basic data structure and the important data structure which is used commonly is linked lists. A data structure where each element contains a reference to the next element is called linked lists, wherein an element which is to next position it contains the address of the previous element. allows for dynamic memory allocation and efficient insertion or deletion in any position. As normal arrays, linked list also allows dynamic memory allocation and insertion deletion at any specific position. Different types include single linked list, doubly linked list, and circular linked list. As we can see here in the diagram, linked list is a data structure which is a sequence of nodes in which each node is linked or connected to the node in following it. As you can see, the first node is called head, and the last node is called tail, and the last node's value is always null. As we keep on iterating, the node has two parts. One part stores the value, and one part stores the address. The first head stores the address of the second, and the second stores the address of the third, and goes on. So the last tail node has the value but doesn't have the address. Address is null. Each node element is called a node. This figure stores two things: an element of the list and the address of the other node. Stacks are data structures that follows the LIFO, last in first out principle. Elements are added and removed from end called the top. Common operations include push element, add element, and pop remove element. As we can see in the diagram, here is an empty stack at the initial moment, and once we push one, it goes to the bottom, and if we push two, it goes on top of one. If we push three, it goes on top of one and two. And if you want to remove the first element, three is always the first element to be removed, and this can be removed using the method called pop. And if you want to push elements again and again into the stack, use the method called push. To initiate stacks, we use the define function heap. For what we do is we create a list and heapify it. After heapifying it, we can use the heap algorithms or the methods to push or pop the elements as per the requirement. Next, queues, a data structure that follows the FIFO, first in first out principle. Elements are added at one end called the rear and removed from the other end called the front. Common operations include enqueue, add element, and dequeue, removing an element. As you can see in the diagram, enqueue and dequeue operations are being performed. Here, unlike stacks, here it follows FIFO, which is first in and first out. So whatever input you give first always comes out first. Heaps. Heaps are specialized tree based structures that maintain specific order, such as max heap or min heap. They allow efficient access to maximum or minimum element. Heaps are used in priority queues and sorting algorithms like heap sort. Hash tables. Hash tables use hash function to map keys to values, allowing efficient retrieval and insertion operations. They provide constant time average case complexity for lookup, insert, and delete operations. Hash tables are widely used for implementing dictionaries and symbol tables. As we know, hash tables include hash maps and hash dictionaries. Trees, a hierarchical data structure with a set of connected nodes. Each node has a parent and zero or more child nodes. Common types of trees include binary trees, AVL trees, and B trees. As you can see here, ABC are parent nodes, and B has two children D and E, and C has two children F and G. Graphs, a nonlinear data structure consisting of nodes, vertices, and edges. Nodes can be connected in any pattern, forming complex relationships. Graphs can be directed or undirected, weighted or unweighted. These are types of graphs, which is directed or undirected, weighted or unweighted. New models of computation. Traditional models like Turing machines are limited in solving certain problems efficiently. New models such as quantum computing or DNA computing require innovative algorithms and data structures. Array and data structure algorithms play a vital role in these new computation models. Quantum computing utilizes quantum bits or qubits to perform computations. Quantum algorithms such as Shor's algorithm or factoring large numbers require effective data structures. Arrays and data structures optimized for quantum computing can improve the efficiency of quantum algorithm. Quantum computing versus classical computing. Quantum computing calculates with qubits, which can represent in 0 and 1 at the same time. Calculate with transistors, which can represent at either 0 or 1. In quantum, power increases exponentially in proportional to the number of qubits. In classical, power increases in a 1 is to 1 relationship with the number of transistors. In quantum computers have high error rates and need to be kept ultra cooled. Classical computers have low error rates and can be operated at room temperature, well suited for tasks like optimization problems, data analysis, and simultations. Si- Classical. Most everyday processing is best handled in classical computers. DNA computing utilizes DNA molecules to store and process information. Efficient data structures are crucial for representing and manipulating DNA sequences. Arrays and data structures designed specifically for DNA computing can enhance and perform at the performance of DNA algorithms. Here are some challenges and opportunities in the field of data structures and algorithms. Developing efficient algorithms and data structures of new models of computation is a challenging task. It opens up new opportunities for solving complex problems more efficiently. Research in this field is ongoing, and advancements in array and data structures algorithms are expected. Hence, we have reached the end of the presentation. Conclusion: array and data structure algorithms are crucial in new models of computation. Efficient data structures allow for faster and more efficient computations. Further research and advancements in this field will lead to improved algorithms and data structures. Before going to references, let's go on and recap once what we have learned. We have learned about arrays. Arrays are fundamental data structures that store elements of the same type in contiguous memory allocations, allowing for efficient and random access. Common operations include insertion, deletion, and search, as we have studied. Data structures algorithms often involve various structures like linked lists, trees, graphs, and hash tables. Algorithms for searching, sorting, and traversing trees structures are essential. For new models of computation, considering quantum computing, quantum algorithms like Shor's algorithm for factorization leverage quantum principles to perform computations more effectively than classical counterparts. Stay updated on emerging paradigms like DNA computing, which uses biochemistry for data storage and processing. These unconventional models explore innovative ways to perform computations beyond classical and quantum computing. And the references I've used for creating my presentation is Introduction to Algorithms by Thomas H. Corman, Charles E. Liseson, and Ronald L. Rivest. Algorithms by Robert Sidgwick and Kevin Wine. Data structures and algorithms in Python by Michael T. Goodrich, Roberto Tamasia, and Michael H. Golwas. Thank you. We have come to the end of the presentation. Hope you like my presentation. Thank you for your valuable time. Thank you.